on the video for today. Because our wireless network is a little bit sketchy right now, I'm running on like a self-contained network from my computer, which has been known to flake out before. If it flakes out hard where it deletes the entire video. Okay? So just so you're aware, if you were planning on going back and rewatching the lecture, you may very well find that it's not going to exist. Okay? Hopefully that doesn't happen, but I just want you to be aware of that. No, I think I'd get yelled at if I ran my computer through somebody else's hotspot, considering it's a district computer. Yeah. So we talked about solubility curves, saturated, unsaturated, and all that kind of fun stuff. And ultimately, all we were really getting at here is that when we go through and run a reaction, if I wanted to react silver nitrate with, and this may be a horrible example because it may be on the very next slide, with aluminum chloride. Both those substances are solids. Okay, so it's not going to be easy to get those two solids to interact with each other because the only place they can interact is on the surface of those solids. So what we tend to do is instead of having them react as solids, we would add water, okay, to make this silver nitrate aqueous and aluminum chloride aqueous. The point being is now each of those individual molecules goes into solution, and now every single molecule within those compounds can interact with every single compound in the other compound. Every single molecule in the other compound. So going into solution can help us speed reactions along. Okay? One of the problems with that, though, is that what would I measure? If I go into the lab now to measure my silver nitrate aqueous, what am I going to measure out? Do you think mass would be something I would measure? Okay. Mass doesn't work because if I measured the mass, I'm not getting the mass of silver nitrate. What am I getting the mass of? Silver nitrate and water. So a mass isn't going to be useful. I could go through and do a volume. Okay? Volumes make sense with liquids, but what am I measuring the volume of? Again, water, not the chemical I'm interested in, the silver nitrate. Okay? And so the issue with taking it into solution is that it now becomes more difficult to measure the amount present. Okay? That's why we can define an extra term. Okay? For instance, if you look at beer versus vodka, they have slightly different effects on the human body, right? With respect to time. Right? Why do they get a different effect?
One's more concentrated.
The concentration of the alcohol, technically the poison, okay, within each of those substances is different. Beer has a much lower percentage of alcohol than vodka. So if you drink equivalent amounts,
You could die.
you're going to have potential side effects come out with the vodka that you may not get with the beer. Okay? So we would have to adjust and take into consideration the concentration of the alcohol within each of those beverages to help us potentially pace or avoid altogether what we're drinking. The same thing's going to happen in chemistry, except we're not drinking it. Now we're trying to get that molecule to interact with something else. Okay, so the concentration becomes important. The issue with concentration is mass a concentration? No. Is volume? No. Is time? Distance? An amount? We don't have a concentration unit yet. Okay? And that's the big thing that comes out of our solution chapter, is that when we look at our chemical reactions, great, I've got a chemical reaction that produces silver bromide. Okay? And we could even switch this around to a different type to have a little more meaning, but this will work. We could look at this reaction and say, well, it's a double replacement. Right? It's balanced. So I could go through and say, well, how much, say, silver bromide is produced? How would I figure that out? Okay, in the lab, what could I do? Just mix the solutions. I have a solid. What do I do to get the solid away from everything else? Filter. I think I heard somebody say that. At least I'm going to pretend I did. Right? We would filter, we now have the solid out. How do we know how much solid I made? Weigh it. It's really easy. I just put it on the balance. There we go. I produced that much. Okay? Where did it come from? It came from the solution. It came from the reaction of aluminum bromide with silver nitrate. Well, how am I going to define the amounts of those that I started with? Remember, the mass doesn't work because the mass is going to include water with it. And water's not doing anything. Okay? All water is doing is helping to mix the things. It's not part of the chemical reaction. Water doesn't show up anywhere in our chemical reaction. Okay? So I can't use mass. I can't use volume because the volume I'd be measuring is more than likely just of water, not useful again. So we have to create a new unit. Okay? And really it's not a unit, it's a conversion factor. That conversion factor is going to relate the amount of our substance per total volume of the solution. So in the case of alcohol, right, in beverages, we're looking at ABV, right? Beer is, depending on the level of beer, let's just say 5%. 5% what? Or 5 ABV. What is ABV? You've seen it. Alcohol by volume. So they took the volume of alcohol per the volume of the whole solution. They gave you a percentage. Right? If we move up to vodka, sometimes they shift it out as proof, but really, I don't know why. Cut it in half, and you now have a percentage, and it's now an ABV. So your vodka is, what are we looking at? 40%? Ballpark? Okay. 40% what? ABV. Again, alcohol by volume. Right? So it's saying the amount of our substance in the entire solution. Well, when we run chemical reactions, we're trying to use the chemical equation to convert substances. Well, what unit do I need to be in to convert substances? Ooh. Does the chemical equation tell me mass? No. Does it tell you volume? Does it tell you time? Distance? No. Well, I just went through most of them. There's only one left. What does it tell you? The count. Okay. The number, like our molecules or our moles. All right, so our chemical equation gives us moles. So instead of doing something like an alcohol by volume, where it's the volume of our substance over the volume of the solution, I would prefer to have the moles of our substance per the volume of the solution. Because if I have moles, I can now convert that substance to something else. Why do we not use moles for, say, alcohol?
Moles is for smaller.
Moles can apply to everything. It's not a bad idea to say smaller amounts. Moles really does apply to everything.
The conversion factor is wrong.
No, the conversion factor would be fine.
Not a lot of people know what a mole is.
Okay, well, we could fix that. I'm pretty sure you ask a 2-year-old, they have no idea what volume is.
We're already using what we're using, so.
Why are we using moles? What's our end goal with moles? To do a chemical reaction. When you pick up a beer, assuming you're of legal age, and you drink said beer, are you thinking, well, there's 5 particles of ethanol in there, and those 5 particles are going to kill 5 of my brain cells through this chemical reaction, and that's going to make me feel like this because of those 5 brain cells dying? Or are you just like, I'm just going to drink it, and my brain cells, you probably don't realize your brain cells are dying. They are, right? Calculated risks, right? My brain cells die off, and now I feel, ooh, floaty, and loss of inhibition. Right? Don't kill all your brain cells, please.
I said that's why I don't drink. I need every brain cell.
Oh, okay, that's good too.
I can't lose one.
Right? We are looking at that as a calculation of how many things are getting killed off, what are we looking at it as? I drink this much and I feel this good, right? Or I feel this bad. So stop drinking that amount, and we find that balance. Some of us find that quicker than others, right? So we aren't running a chemical reaction to do that. All we're doing is just based off of how we feel. So we don't need to know an amount of each of those substances because we aren't doing a chemical reaction, okay? At least not consciously. Why does chemistry need the mole amount? Because we are doing a chemical reaction. So it just depends on what we're doing with that information. Okay? For alcohol in a beverage, we aren't concerned about doing a calculation with it. So we don't need that extra information. All we care is a ballpark number that gets us an idea that we can then estimate later on, usually through trial and error, mostly error, okay, what is an appropriate amount or not. Okay? Here, we need a numerical amount because we don't have a, well, I feel like this was a good enough amount of product to produce. That doesn't work. We need to quantify how much. We need a numerical value tied to it, which means I have to use an amount. Okay? Why not use grams? Well, does the chemical equation tell us anything about grams? No. So it's again coming back to what we're using the concentration for. We're trying to use this concentration to convert from one substance to another. And that substance conversion requires the count unit of moles, which means our concentration is going to be measured as a moles of our substance by a total volume of that solution. Okay? This is now known as molarity. Okay? Just like when we looked at mass per volume, we called that mass per volume density. Okay? Well, we've all used density. All we're doing is introducing effectively another form of it. Okay? We're now using an amount per a total volume. Okay? With density, we always specified those units of grams per milliliter or grams per liter. With molarity, for whatever reason, you'll typically see molarity written out as, say, well, 3 capital M. What is the capital M referencing? Molarity. Okay. Have you ever seen the unit capital M show up yet?
Yes.
Really? Okay.
Yeah, the 1.0 M is one of the
1.0
that we're using in lab.
Okay. If we think back to our exposure in lab, you probably have seen this capital M unit. Okay. But this is lecture. Don't use that. Fair point, though. Okay. Have we seen the capital M unit show up in lecture? No, it hasn't shown up in any of our conversions. That's because it doesn't get used. What does get used? Well, moles and liters. So the instant you see capital M, what you should be rewriting this as is now moles over liters. What's the number in front of liters?
1.
1, because if it was anything other than 1, what happens to the 3?
Changes.
It changes. Okay. Why is this now helpful? Well, what do I have? 3 moles per every 1 liter. I have a conversion factor that can now allow me to convert between moles and volume. Okay. That becomes really important. That's kind of like how we would convert between molecules and moles, or grams and milliliters, or moles and grams. Okay. We now have another conversion factor that you have to manipulate and use. Okay? That is all it is. But you do have to remember this extra little tidbit because it's almost always written as just a capital M. The instant you see capital M, convert it into our standard numerator-denominator, top-bottom fractional unit system, and you now have a conversion factor. Does it have to get written as 3 moles over 1 liter? No. How else could it be written? 1 liter over 3 moles. This is the same relationship, but now I'm using the conversion factor differently. Okay? Now what I'm trying to do is get rid of the mole unit so that I can end up with liters on top later on. So depending on what I'm solving for, and this is where you could say multiply and divide, I'm either multiplying or dividing by the molarity. If we just recognize it as a unit factor, I can place it wherever I want, either top or bottom. And as long as I make sure the numbers stay tied to the correct unit, everything's good. Kind of makes sense? Do you want me to work one with you? Okay, so we'll go through and do this one, beginning to end, fully correct. Okay, because that's been recommended or suggested that I do, so let's go through and do that. What is the molarity of a solution containing 24.0 grams of sodium hydroxide in a 0.100 liter solution? Okay, so what am I solving for? I'm solving for molarity. Okay, so my capital M would be molarity. But I've written capital M. What does capital M mean? Moles over liters. Okay, those are the units, the numbers that would need to go in. I need to know what number to go with moles. I need to know what number goes with liters. Okay. Yes, one will eventually go with liters once I've done the calculation, but I have to do the calculation first. Okay. So I need to know a mole amount and I need to know a liter amount. Okay? In my given information, what else do I have? And actually, let's take a step back. Let's go back to our moles, because this has to do with our units. Okay, what I've provided are the measurements. Every unit is incomplete until we also specify
Substance.
the substance. Moles of our sodium hydroxide, liters of solution. For those of you who want abbreviations, SOLN usually works pretty well as a solution. Okay? Or you can write out solution. I'm fine either way. But I'm going to write SOLN. Okay? So, what other given information do we have? Okay? 24 grams. I'll partially accept that because all you've given me there is the number and the measurement. What's missing? The substance. Are you told the 24 grams of something? Yeah, so we do have the substance tied to that. So I have, as given information, 24.0 grams of substance. What else am I given?
0.100 liters of solution.
I'm given 0.10 liters of solution. So I know what I'm solving for now, and I know what information is given. So I can now set up my process. So in my process, the far right, I want moles of sodium hydroxide per liters of solution. So now where do I want to start this? Okay. I need to find either moles of sodium hydroxide or liters of solution in my given information. I don't see moles of sodium hydroxide. Okay. So I will hold off on that one. I do see liters of solution, right? Directly given to me. Where do I want my liters of solution to show up in my answer? In the denominator, which means that given information should show up where? In the denominator, in the bottom. So 0.100 liters of solution. What is that being converted to? If we look at the given information, 0.100 liters of solution, what is that being converted to? What other unit is showing up in that given information? In the given information for that number. Okay. Said another way, because I've color-coded this, each piece I've changed the color on, what other unit is written in blue? What's that?
Liters?
Liters of solution. I already wrote that. What other unit? There isn't one. So what shows up in the numerator? 1. I'm not converting it to anything. It is a given piece of information. I just want that given piece of information to show up in the denominator. There's no other thing associated with it, so don't put anything above it. Okay? Now I'm kind of stuck because I need to get to moles of sodium hydroxide and I don't have that unit. So that one is now used, so I don't need to use it again. Okay? What do I have? I have grams of sodium hydroxide. Not moles, but grams. Okay? Which means I'm going to need to do a conversion. Okay? Before I get too far into that conversion, do I need to do another one? What is the substance? Sodium hydroxide and sodium hydroxide. So I don't need to do a substance conversion. All I need to do is a measurement conversion. Okay? But I need to set this up and make sure I place it accordingly. Where should my substance show up? Does my substance and my answer show up on top or on the bottom? On the top, which means where should my substance show up in my starting calculation? On the top. Whoops. What color did I use? Blue?
Blue.
No, I used purple. Hot. Just wanted to make me erase again. Grams of sodium hydroxide. What number is associated with that grams of sodium hydroxide? 24.0. What am I converting that grams of, or in that given information, grams of sodium hydroxide, what am I relating those grams of sodium hydroxide to? I like where your mouth is moving. Nothing. That's it. Grams of sodium hydroxide, which means what shows up in the denominator? 1. Because I do not want to change the meaning of the unit given or the number given. Okay? So I've now taken all my given information and input it into the question. If I ran this calculation, this would just be 24.0 grams divided by 0.1000 liters, and I'd end up with not the answer. Okay? Because the units aren't correct. So what do I have to do? I have to do a conversion. I'm solving for the molarity. In that conversion, what needs to happen? Should anything happen to the liters of solution unit? No. Why not? That's exactly what I want, and it's in the exact location. So I don't want to touch the liters of solution unit. How about the grams of sodium hydroxide? That needs to disappear. I don't want grams of sodium hydroxide. So in my conversion factor, I'm going to have to put grams of sodium hydroxide on the bottom. I don't know what number to put there yet. Okay? If I put in the 24.0 grams, all I'm doing is undoing what I've already done. Okay? So I'm saying I shouldn't have done that to begin with. Okay? We don't know that necessarily yet. Okay? What do I want to get to? I want moles of sodium hydroxide. So I now have a conversion factor that relates grams and moles. Does that conversion factor exist somewhere? Yes. Where does it exist? Avogadro's... Fudge. You got me saying... I said fudge. You got me saying the G and the C at the same time. Avogadro's number relates what to units?
Grams and the...
Does not relate grams. Atoms and moles. It's a count. Avogadro's number is literally just a count. It's not a mass. Remember, it's Avogadro's number, no mass. Okay? So that would be the number of particles equals a mole of particles. Okay? If you were sent to the door, to the store to buy 12 dozen eggs, do you buy 12 grams of eggs? No. Okay, I don't know how much an egg weighs, but I'm pretty sure it doesn't weigh 1 gram. Okay? So the whole point is to not relate mass, but the number of particles. That's why it's Avogadro's number. Okay? This is a mass unit, so that can't relate to moles. Where do I find the mass to mole relationship? That is off the periodic table. How would I go through and solve that? Well, sodium weighs, because I'm lazy, 23 grams per mole. Oxygen weighs 16. Hydrogen weighs 1. I add that up, 40 grams per mole. Thank you for doing the math. Okay. What does the 40 show up next to? Grams. So where should the 40 show up in my equation? In front of grams, which happens to be in the denominator. What shows up in front of moles? 1. What happens? Grams of sodium hydroxide cancel. If I run this calculation as written, what do I get? Fair answer. I don't want the number, I want the units. Moles of sodium hydroxide shows up in the numerator. Good. Liters of solution shows up in the denominator. Is that what I want for an answer? Yeah. Because that's good, I can now run my calculation. I take 24.0. Okay, so since my units match up, what I would then go through and do is say 24.0 times 1, so that's easy. And then I would also go through and do 0.1 times 40. I would enter those independently into the calculator and then do the division, okay, which allegedly comes out to be 6. Yes, it does. Is 6 correct? No, because sig figs. What does our answer need to be? 6.00. 3 sig figs because of our calculation above. Okay, so when I show your work, that's what I would expect to see beginning to end. Make sense? Okay. So we didn't do anything incorrect in that solve and then undo it later. We just went through and ran the calculation as was. Kind of make sense? Okay. So now that you have your example, your turn. Or wait. Questions about what's written up there before we make it your turn? Okay. How many grams of potassium dichromate? Don't worry about not knowing the name of that. Are in 125.0 milliliters of a 0.150 molar solution of potassium dichromate. Okay? So, good first step, identify what you're solving for, identify the given information, and then start to organize that information into our standard format. Okay, what do we want as an answer, what are we given, and start setting up the units accordingly. Okay, see how far you can get in 2 or 3 minutes. This number. Right. Typically when you go through and see these, they're very nicely, cleanly separated. Okay. This is 125 milliliters of what? Of solution. That solution happens to be what concentration? 0.150. Those two things are independent pieces of information, which is not necessarily obvious. Okay? But that volume measurement is not the same as the liters. Okay? Those are independent pieces of information. Okay, even though they are written in such a way that they look tied. English language can do that to you. Okay, so we have to be careful with our interpretation of what the language means. What are we solving for? Grams of potassium dichromate. So in my setup, I want grams of potassium dichromate in my final answer. right? Now I need to use some of my given information. Okay, well, what given information do I want to start with? Right. It is entirely up to you. Right. I heard a couple people suggest we could start with the 125.0 milliliters of solution. Is milliliters the proper measurement that I want? No. Is the solution the proper substance that I want? No. Okay. So believe it or not, you're not wrong. You could start with the 125 milliliters of solution. However, why did you start with it? What was your reasoning? Anybody that started with it want to volunteer a reasoning? Okay. I can tell you why most people would start with it, because we think the given information needs to show up in the numerator, so I would just start with it in the numerator. So the reason you're placing it there is because you've solved a question like this before and you've memorized how to solve it. That's fine, as long as you don't screw up your memorization. Okay? This is why I would argue what you should do is focus on what you're trying to get to and start with something that keeps some of that information. Okay? So 125.0 milliliters of solution doesn't keep any of that information for my final answer. It doesn't have the right substance. It also doesn't have the right measurement. So I want to start instead with the red one. Okay? The red one doesn't give me the right measurement unit either. It gives me moles and liters. I don't want moles or liters in my answer. But what do I want? I want the potassium dichromate. So I want that substance. Where should the substance show up in my answer? In the top. Which means when I go through and use this red number, where should the substance show up? On top. Okay. I'm going to be a little bit weird with the order here. So my substance was moles of potassium dichromate. The unit on the bottom was liters of solution. The number associated with this was 0.15 moles, 1 liter. Yeah? So those of you that did not start with that number, in your later calculation, is that how it was written in? Yeah. Okay. So we look at this. Is moles of potassium dichromate what I want? No, what do I want? Grams of potassium dichromate. So what has to happen to that moles unit? It needs to be gotten rid of. It needs to be converted into grams. So the moles of potassium dichromate needs to show up on the bottom because it's trying to cancel. What unit do I want to show up on top? The grams of potassium dichromate, because that's what I'm trying to get to. Where do I find that conversion factor? That goes from the periodic table. Avogadro's number is, again, a count, not a mass unit. It's not a measurement. Okay. Okay. So because Avogadro's number has come up a couple times already today, okay, Avogadro's number is a useful number when looking at a count of particles. How many times do you want to count 6.022 times 10 to the 23rd particles? Okay. This is a good question for silence because no one ever wants to do that. Okay. How many times would you measure out a single particle? This is a good time for silence as well. Never. You would never do that. Okay? So Avogadro's number is insanely useful in the fact that it scales everything up to an amount that we can work with. Okay? Do we have to use Avogadro's number to do that scaling? It's behind the scenes. How many of you know how to program a computer? How many of you know how to type in a Word document? Come on now. Okay? How are you able to type in a Word document if you don't know how to program a computer? The programming in the computer is what's allowing you to be able to type in that Word document. The reason we can go through and do these calculations is because of Avogadro's number. That doesn't mean I need to use Avogadro's number to be able to do these calculations. So it's running in the background. It's the programmer's job to run it in the background. Smarter chemists went through and said, let's get rid of this whole horrible molecule system and scale it up to a system that we can use. That system we can use allows me to do these conversions much, much quicker and efficiently without having to dig down into the programming or using Avogadro's number. So the only time you need to use Avogadro's number is when you're looking at single particles. If you're asked for how many molecules or how many atoms, then you got to worry about Avogadro's number. Otherwise, we don't care. Right? In the lab, how many times do you measure out single particles? You don't, which means you never use molecules or atoms. It's part of the framework that allows us to do our calculations, but it is such a rare circumstance to ever deal with things on the molecular level that we don't have to worry about it outside of Chapter 8. Yeah, it's kind of neat, isn't it? Right? So it's an important concept, but it's not an everyday concept. This is one of the reasons why when chemists get all excited about Avogadro's Day or whatever that stupid day is in October, okay, I'm like, whatever, who cares, because I don't need to use that number. It's an important number to acknowledge its value for, but it's not something that we use every day. What will we use every day? Moles. How do we get moles? That was Avogadro's number. Right? But I don't have to work with Avogadro's number to deal with anything because the beauty of that number converted the periodic table up into measurable units. Right? So I can go to the periodic table to get my grams per mole. I would do that by taking the mass of potassium at 39.1, but times 2, because there's 2 potassiums, plus the mass of chromium, 52, close enough, times 2 plus 16 times 7. And if we do all that math, carry the digits, flip around, it comes out to 294, cross multiply, divide, 2 grams per mole of our potassium dichromate. That looked much cooler probably in the video because you're like, wow, how'd you pull that one off? Thank you, Evan. Okay, so our 294 shows up in front of grams, 1 shows up in front of moles. Okay, what happens? The moles units cancel. And I now have grams of potassium dichromate. What did I want? Grams of potassium dichromate. Awesome, I'm there. Good. I still have the liters of solution that I don't want in my answer. Okay? So I would have to do another conversion to get rid of that. Notice how I placed this. There's a suspicious space floating in front there. I want that liters of solution to disappear. Okay? And I want to place it on top. Am I given the liters of solution?
Yes. No.
No, I'm given milliliters. So I can't get rid of liters of solution or place a numerical value there. I'm going to have to do a conversion factor. Liters of solution to?
Milliliters.
Why'd you pick milliliters? Because I know I have milliliters given in the answer. What numbers show up with this liters and milliliters? 125.0 would work for milliliters of solution if it was only milliliters of solution. Is this only milliliters of solution? No, this is milliliters of solution related to liters of solution. What numbers need to show up in there? Nope. What do you have in the back? No?
Where did you get 1,000 from?
Okay. What does milli mean?
1,000.
1,000th. 10 to the negative 3. The power of 10 always goes with the core unit being liters. 1 would go on the bottom. Okay? That is how I've been training you to do it. Just because people haven't been doing the way I've been training you, that's okay, as long as you do it correctly. Right? So what he went through and memorized was that 1,000 milliliters is equal to 1 liter. That's the exact same calculation as this, just flipped. Okay? What happens with our units? Well, liters of solution disappears. Awesome. I didn't want liters of solution. So now I have my answer. No, I still have milliliters of solution floating in there. What can I do to get rid of that? I now need milliliters of solution in the numerator so that that unit would cancel. Am I given milliliters of solution? Yes. 125.0. What shows up in the denominator? 1. Because if I look at my given information, there's nothing in the denominator, which means it has to be 1. So those of you that started with 125.0 milliliters of solution, did it need to show up in the numerator? Yes. The reasoning, again, that I don't like showing that is why did you place it there? If you're placing it there just because you think it should be there, that's a 50-50 coin toss that doesn't work. Okay? If you get the answer right, I can't complain. All your work's correct. Okay? That's why I would, again, start with the red and then work forwards or work backwards. Why can we work both directions in this calculation? Multiplication is communicative, which means it doesn't matter the order that you run it in. So this was given. You had to memorize your milliliters liters conversion, and then this was given. Make sense? Hi. Did anybody actually solve that out? Because some people like numbers. Did you solve? You tried, but you didn't get a number. What'd you get? 5.516 grams. Can I get a second?
516 grams. Yeah, that's what I got too.
All right, we got a second on 5.516. If we take a look at the numbers, I think I believe that. I think that seems reasonable. Okay. Would that be a correct answer? No. What's the issue? I do have the grams. It's sig figs. This has 4 sig figs. Doesn't 125.0 have 4 sig figs? Yeah, it does. Why is my answer wrong? The molarity was also given information, and how many sig figs are in that molarity given? 3. This leading 0 doesn't count. Go back and check your sig fig rules. It's okay. 3 sig figs, which means the answer is not 5.516. It is 5.52. We have to round because that 6 was 5 or greater. Whew. Questions? Okay. That's pretty much the level of calculations that you're expected to do with molarity. Okay. Those of you that have the slides printed out might see what's potentially coming. Sorry?
I think it's in malaria.
No, I said molarity. A chemist needs to determine the concentration of a solution of nitric acid. She puts 745 milliliters of an acid into a flask with an indicator. She then slowly adds 0.200 molar of barium hydroxide to the flask until the solution changes color, which indicates the equivalence point. We haven't talked about the equivalence point. The equivalence point means that the moles of hydroxide equal the moles of hydrogen ion. Okay. She notes that 165 milliliters of barium hydroxide was needed to reach this point. What is the molarity of the nitric acid? You have the complete and utter full ability to answer this entire question. Okay. It is a bit daunting, okay, because there's lots of stuff going into this. So the reason for that little internet meme thing there is the way I've done this in the past, which was really, really kind of evil, is I had people come up with the process. you needed to outline the process on how to do this. Okay? Once you had the process, okay, so don't worry about the extra points, that's irrelevant. Once you had the process, okay, you then have to go through and make sure you can solve without deviating from that process. Then what would you do? You would pass that process to another group. That other group has to follow your process to solve. Okay? If they follow your process correctly and get to the correct answer, then and only then would you get extra credit. I've tried this 2 or 3 semesters. In those 2 or 3 semesters, you know how many groups came up with an accurate process? 1. Yeah. The amount of stuff that you have to cycle into this is pretty daunting. All right, so let's go through and think about what we would have to do. Whoa! What we would have to do. Okay. Okay, the whole point was to solve for the molarity, right? Molarity of nitric acid, so capital M, HNO3. Capital M you should immediately write as moles of HNO3 over liters of HNO3. Okay? We again don't know what those numbers are. This is not one we're going to solve all the way out. But what other information is given?
The milliliters of acid in the flask.
745 milliliters of the acid, which is our HNO3. Our HNO3 solution, we should actually say. What other information is given?
And then molarity of the barium hydroxide.
We're given 0.20 moles of barium hydroxide per 1 liter of the barium hydroxide solution. Okay. We have to include the barium hydroxide unit in that solution because we have 2 different solutions. So we have to be careful to make sure we don't overlap those incorrectly. Okay. What other given information do we have? We're also given 165 milliliters of barium hydroxide. So just writing down the given information, you'll note I've actually already done some interpretations. Some questions had to get answered right away. For instance, nitric acid is HNO3. Barium hydroxide is BaOH2. Okay. If we go through and look, the units I want is moles of my substance, right? Moles of what substance? Nitric acid. Am I given moles anywhere in my given information? Does anybody see moles written in the given information? Yes, but it's given for a different substance. So what am I going to have to do? A conversion of substance. How do I convert substances? Using moles, where do I find the numerical values to do that conversion? No. The periodic table is great for determining the mass per moles of a single substance. Where do we find the conversion factor to convert substances? If I give you 2 wheels, how do you make a bicycle?
A frame.
You need a frame. What did you use to determine that? You know how to build it because you have a recipe for that, which some people will call common sense. Okay? So if we really want to go that way, to figure this out, we would need a chemical equation for this, which is common sense. You should totally know the chemical equation for this. Yeah, it doesn't work quite as nicely, does it? Okay. How would we get the chemical equation? What are we reacting? Nitric acid with barium hydroxide, which needs to produce something. Are we told what it produces? Products. What are the products? Are we told what it produces? No. Are you required to know what it produces? Yes, because this reaction is a double replacement or neutralization. Either way, you're required to know what it produces. So you would have to predict the products, being, we'll write it out as HOH and barium nitrate. In the process of doing that, we'd have to realize that nitrate is a -1, barium's a +2. That needs to be BaNO3 2. Right? There's our HNOH, or HOH. Yeah, that didn't work. Okay. Hey, there you go. That makes it totally legible. Okay. Is that equation balanced? No. So what would we have to do? Balance the equation. Once we have the equation balanced, now we can convert substances. Okay? Oh my gosh is a valid answer to this. Okay? At any point have I talked about anything that you haven't already done? No. You're responsible for all of these individual pieces. If you have to move into 151, they pretty much expect you to do this from the get-go. If you don't have to move into 151, don't worry about it. We don't make you do this level in lecture. We do make you do it in lab. Okay? So we have to be thinking about what information is given, what do I need to convert, what things need to cancel, and it's a question of slowly building up your solve to get all the way through it. Yes, that is challenging, but you can do it. It just requires practice. Okay? If you want to see this full solve, talk to me after class. It's not important enough that I want to spend any more time talking about it. What I do want to do is move through onto some slightly more content. Okay? What are we doing? What have we spent the last 2 or 3 weeks doing of this unit? Conversions. Okay, that's it. We set up our conversions using what I reference as dimensional analysis. Your textbook calls the unit factor method. All we're trying to do is come up with relationships or find relationships between different substances so that our units cancel. Okay, that's it. I don't have to know the meaning of any of those things. I just have to recognize the utility of dimensional analysis. I can go through and solve a lot of physics problems now, even though the last time I took physics was, wow, probably 15 years ago. And I could probably do a passable job in physics just because I recognize the utility of canceling units. Because that's all you do in physics, is convert units. Right? All the equations that you think you need to memorize are just a form of dimensional analysis. Okay? What is our setup? Write your desired measurement and substance, so your official unit. Write down your given measurement and substance. Okay? We need to be smart about the given measurement and substance to place it in a location that makes sense for what we're trying to get to. At that point, I now need to come up with conversion factors that allow me to convert between those either measurements or substances or both. So it's a question of finding those conversion factors. Well, where do you find those conversion factors? If we look at those conversion factors on the front of the exam, they're always given in this format. Okay? Why do we give it in that format? Because if I say A over B, well, then you have no clue how to convert B into A. Okay? This format gives you both conversion factors. It gives you the ability to go A over B or B over A. Why? Because from this equation, if I divide one side by the other, what's left over? 1. So now I can input that factor into any conversion I want, and all I'm doing is multiplying by 1. But that 1 allows for the units to convert across. Okay? So it's given in an equality statement, not in the fractional statement. Okay? So what are some conversions? I don't know any conversions. I got one for you. 1,000 milliliters is 1 liter. Where did that come from?
Metric system? Or just...
It's a conversion factor from the metric system, okay, which in theory came from, now, on a test, your brain, because you're required to memorize it. Okay? For this next test, you're allowed a flashcard. Okay? So now it doesn't have to come from your brain, it could come from the flashcard. But you're now also using up valuable space on your flashcard for something you should have memorized. Okay? What's another conversion factor?
3 feet, 1 yard.
3 feet, 1 yard. Where did that come from?
Brain.
Your brain. Another conversion factor. One gram per 1 mole. What did I just describe? It's not. Oh, God, you're going to start getting stuff thrown at you, dude. What did I just describe? 1 gram per 1 mole. Molar mass is the unit, but what's the substance? One gram per 1 mole.
Gram per mole.
That's, again, the unit. What's the substance?
Yes, yeah, you didn't say.
With that information, it is implied that you should be able to figure it out. Where do we find the information about grams per mole? The periodic table. When we look at the periodic table, there is only one possible answer that gets you 1 gram per 1 mole. A hydrogen atom. Okay? So you need to use the periodic table. What if I want to convert the moles of one substance to the moles of another substance? Periodic table is just substances. To change substances, I would need a chemical reaction to show how those substances convert between each other. Okay? So I need to be thinking about not only what are these conversion factors, but where did they come from? Where do I find them? Okay? Some of it can be written down on your note card. You could provide the conversion factor between grams and moles for every single element you can possibly think of, and every single compound you can possibly think of. You won't need a note card anymore. You'll probably need a textbook. Okay? So knowing where that information is found is more important than knowing the information. Okay? We always have a periodic table because we're freaking chemists and we're awesome and we always carry one with us. Yes, I do. Yeah, phones are awesome. You've got an app. You can just put it on an app. I used to have a paper version. I don't anymore. Okay? So we have to know where this stuff is found. We've been constantly cycling through where it's found. Okay? Periodic table, atomic, molecular, or molar mass can allow us to potentially convert between atoms and AMUs. Okay? That is an insanely rare conversion to use, okay? But we could do it. Why do we not use it? AMUs is a measure of weight, mass. Okay? What balance measures in AMUs? None, because that is the mass for an atom. Do we work with atoms? No. That's our background programming. Okay? We rarely deal with that. But if I'm going to now move into atoms, can I scale that up to grams? I can through another conversion factor, one we haven't talked about. Guess what this conversion factor is? Pretty close. Okay? If you go through and manipulate these numbers, get this 1.661 times 10 to the minus 24 over to the other side. Okay, so you'd have to divide both sides. 1 divided by 1.661 times 10 to the minus 24. So 1.661 times 10 to the minus 24 into 1 fits 6, 0, 2 times 10 to the 23rd. So let's try that again. Let's do that a little faster because I kind of lost track of that. I believe it was 6.022 times 10 to the 23rd.
Yeah. Ain't that right?
What? What was that number? That was Avogadro's number. I didn't do any calculation. I know that those things are related. This conversion factor between grams and AMUs is Avogadro's number. Okay? It was really cool, wasn't it?
I
Yeah.
like how you're up there like, oh,
I
yeah.
know.
How do we convert between grams and moles? Well, that's a periodic table. How do we convert between moles of one substance, A, to moles of another substance?
Balance.
Our balanced chemical reaction. So we have ways to find that information. We have to recognize where that information is found and pull it and use it. Okay? This is another different way to organize that same thought. How do we convert measurements? Okay? You get tables of them in your book. Some of them you're supposed to memorize. English ones I give you on an exam. Okay? The number of atoms. Okay? We can pull that from a chemical formula. Okay? There are 2 sodium atoms per 1 molecule of sodium sulfate. That information is found in the formula. How about number of molecules? Right? If I want to convert the number of molecules from one to another, from a balanced equation, moles, formulas and equations both give you that. Okay? Ultimately using Avogadro's number. Atomic, molar mass, all of those things are found there. It's a question of recognizing, do you know where that information is? Okay? Once you know where it is, all you have to do is use that information with the information that I told you to learn in Unit 2. You mean that dimensional analysis stuff that I didn't want to learn because I thought it was stupid? Yes. That stuff with these units. That's what you're trying to do. Okay? So if you had a hard time within Unit 2, this unit becomes more difficult because you're required to know where these conversion factors are found. Okay? So exam time. What could you potentially put on your exam, or for that matter now on your note card, to help you with this? What are some useful conversion factors?
1 liter equals 1,000 centimeters cubed.
Okay? So we could write on our exam, 1 liter equals 1,000 centimeters cubed. Is that going to be a useful thing to write down on our exam? No, why not?
It's already there.
It's already there, so don't give me something that's already there.
Avogadro's rule.
Okay?
That's not there.
Avogadro's number technically actually is on there, but it's written in a unit system that you may not like. So 6.022 times 10 to the 23rd atoms equals 1 mole, technically, of atoms. If you prefer to see it that way, great. If you say, well, I don't like atoms, I like molecules, then go ahead and write it as molecules. Okay? You now have that extra information that you don't have to think about. Okay? What other conversion factor might you want to use? How do you convert between grams and moles? What's that? No.
What's that other?
Where do we find the conversion factor between grams and moles? So now when you go through a conversion factor, if you've been following the method and you wrote out grams and moles, you're like, oh crap, I don't know what to do. You could go to your front or your note card where it says grams equal moles, periodic. Periodic what? Table. Oh, there's the periodic table. Now I know where to find those numbers. There it comes from. Okay. How could I convert, say, the moles of substance A into the moles of substance B? That comes from the chemical equation. So by including some of this information, notice there's no numerical values here. Why no numerical values? Depending on what substance you're looking at or what chemical reaction you're looking at, what happens to the numerical values? They change. So I don't want to include numerical values here. What I want to include is the units that allow me for that conversion. I now also know that the numbers come from the chemical equation. Okay? So I'm trying to provide myself hints to go through and solve. Kind of make sense? I kind of have high hopes. Don't crush my hopes. Okay? Please. Okay, and you guys are ready for the exam next Thursday, right? No, it's not. I was just kidding. In a couple weeks.
I was ready.
Chapter 10. We get a bunch of stuff in gases. It's in 2 weeks, I think. Chapter 10 in gases. Right? Gases is not officially part of our curriculum, but it is so incredibly important to chemistry that we need to talk about it. So somebody made a massive oversight by not including it. Every campus I've ever talked to that teaches this class talks about gases. So this is not something that I'm just forcing you to do. Right? And believe it or not, in theory, I could cover all of gases in the next 2 minutes. Right? I'm not going to do it that fast. Right? Properties of gases. We've got a bunch of general properties that you're probably already aware of. We talked about the variable shape and volume. We've also talked about their compressibility. Right? Why are they compressible? There's a lot of space in between. So the number of particles in a given volume is very tiny, meaning I have a low density. So all of these facts are things you already know. It's just a question of applying that information. Okay? Another piece of information here, gases will mix uniformly with other gases. Because there's so much open space and they're constantly moving because they have insanely high kinetic energy, they mix very, very well. Okay? As opposed to two solids. I put two solids near each other. How well do they mix? They don't mix because I don't accept their solids. Why can't they go between each other? There's no space between the individual particles. They also aren't moving, which makes it difficult for them to interact with each other. Right? The next big thing that gases have that most other substances don't is that gases exert a force on the container that holds them. Okay? This is why if you took a compressed gas cylinder and you stuck your mouth around it and opened it, you would die. Okay? Because what happens? The gas comes out. The container holding the gas was a giant metal container, right? Holding back that pressure. When you open it up, where does all that pressure go? Into your lungs. Your lungs aren't made out of giant metal cylinders. They can't withstand it, and what happens? Your lungs explode. Okay? That's kind of a bad thing for life.
Is there any coming back from that?
No. Okay? The next part that kind of comes up is that we follow something known as ideal gas behavior. Okay? We can go through and say, this is how people should act. Does that mean there's nobody running around killing people?
Probably not.
Really? There's lots of people running around killing each other, right? Okay, that happens a lot. Okay? You're not supposed to do that. Okay? Ideal people don't do that. Okay? But if we mimic our world environment based on those few people, then what happens to the interaction in this classroom? Is anybody going to come to class if you're afraid everybody's going to knife you, including your teacher? No, we have to mimic it off of an ideal environment. Okay? In our ideal system, okay, what we're hoping is that people act civilized. And we base our worldviews off of that civilized interaction. Because if we base it off of the outliers, we don't get a real system or an ideal system. We do the same thing with gases. We mimic certain things and we say, most gases act in this way because it allows me to model their behavior much more efficiently. Okay? We'll pick up there, what are we, Thursday now? We'll pick up there.